Welcome back, dear students, to the tetrahedron chemistry classes. So in today's class, I am going to solve three different problems or based on the combined spectral problems, and these problems I have taken from the spectroscopy book written by the Pavia and Csir, and these problems I have taken from the chapter number 3. The following compound with the molecular formula C8H11N shows a doublet at about 3350 centimeter inverse and bands in the range of from 1600 to 1450 centimeter inverse in the IR spectrum, and draw its structure. Okay, and this is the proton NMR spectrum, and this if you carefully look this proton NMR spectrum, then you can quickly jump up to the conclusion that this molecule is having a benzene ring. Why? Because we are having a multiplet kind of the signal resonating at near about 7.1 ppm, which is clear cut indication for the presence of the benzene, right? And then you are having the pair of a triplet. Two triplets are given here in the range between 2 to 3, more precisely somewhere at 2.6 and 2.8, right? And then you are having this particular singlet. Okay, and if you read the information given in the IR spectrum, which is doublet at 3350 centimeter inverse. So the student who knows the interpretation of the IR spectrum, they may quickly jump up to the conclusion why this doublet is here. But if you don't know, don't worry, I'll come to this point a little later on. Okay, and then there are the ranges of range of bands from 1600 to 1450 centimeter inverse, which is, you know, due to the presence of the double bonds of the benzene ring. Okay, and you need to draw the structure, most probable structure for this particular compound. So as my usual practice, what I will do, first of all, I'll calculate the hydrogen deficiency index, because this compound is containing nitrogen. So I have expanded this particular formula in my earlier classes where only hydrocarbons or the oxygenated hydrocarbons were there. In those cases, I have used the little compressed formula where I didn't include the nitrogen and the halogen in the formula, but here I am including the nitrogen as well as the halogen. So how we can calculate 2, which is a constant, and number of carbons given in the question is 8, right? So it is better to write C8H11N. Okay, and then plus 2 is there, and one nitrogen is there, so you will add 1 to it, right? And then minus 11 minus 0, right? And then you will divide it by 2 according to the formula. So what you will get, 8 to the 16 to 18 and 19, this is 19 minus 11, okay, divided by 2. This will give you simply your 8 by 2 equals to 4, right? So hydrogen deficiency index is 4, and this is the perfect fit for the benzene. So these are the 3 double bonds and 1 ring. Okay, so this is perfect fit for the hydrogen deficiency index of 4 actually. Okay, so what is the meaning of the 4? Your molecules may have 4 rings, which is not possible in this case. Your molecules may have 4 double bonds, which is again not possible in this case. Okay, why I am saying that this is not possible? Because I am having the information from the proton NMR spectrum, benzene ring is there, so there is no probability of the 4 double bonds. So what other options are? Other options are uh, 1 ring plus 3 double bonds. This is the perfect fit for the benzene, which is also confirming from this proton NMR spectrum. So first of all, this thing is quite clear that benzene ring is there. Now what you can see, because you are having the nitrogen, so there may be the presence of 2 different kinds of the functionality here. First is your carbon triple bond nitrogen, okay, and second is NH2, right? And for the beginners, this may be this may be the great confusion for them. Okay, but if you know the IR spectrum and the concept of the hydrogen deficiency index, so based on this, you can quickly discard the possibility of the CN ring. Why? If along with the benzene ring, CN is also there, then the hydrogen deficiency index must be 6 or the 7 for this one, right? 6 or 7, you can calculate it, but it is only 4 here, right? So that means this cyanide is not there. And one more very important thing is that if cyanide, say if cyanide was present in this particular compound, then definitely we would have we would have the band in the IR spectrum which will resonate somewhere around 20 to 60. So this is the range for the cyanide, 2260 to 2210 centimeter inverse, right? But this band is not there in the IR spectrum, because in the IR spectrum we are having the band at 3350 centimeter inverse, and between the 1600 to 1450 centimeter inverse, and the information about the cyanide is missing in the IR spectrum, so we can discard this particular thing. Okay, so now you are having the two fragments. First fragment is benzene ring, and second fragment is the NH2 group, right? So this is the most probable. In a little while, we will also confirm why this NH2 is there. Some other informations are also there, right? And then you can see here two triplets are there. One and two, two triplets are there. So how we can get the two triplets? The only possible way is that my CH2, if connected with the another CH2, so this will give you the triplet. If you want to calculate the splitting pattern for the this methylene or these two hydrogens rather, right, then you will apply the n plus 1 rule. So according to the n plus 1 rule, what will happen here? N is the number of neighboring hydrogens, which are 2 in this case. So what you will do, you will put 2 here and plus 1, that will give you 3. So this will produce a triplet in the proton NMR spectrum. And this triplet and this triplet is there in the proton NMR spectrum. And similarly, if you want to calculate for this these two hydrogens, so again in the neighbor two hydrogens are there. So for this again you will apply the n plus 1 rule. Okay, for beginners I am writing it again, right? So again it will be 2 plus 1 equals to 3. So you are getting the two triplets. Okay, so second fragment is this one. Okay, this is fragment number 3. So in short, you are having these three fragments. And if you count the total number of carbon atom, 6, 7, 8. So this is C8, 11 of your hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Because this will be mono substituted, you will have only 5 hydrogens on the benzene ring, right? And so you are having these three things. And now you can conclude your structure what actually we are having. So if I put the pieces together, uh, I'll have this thing. We left with the interpretation of the IR spectrum. So here you are getting a doublet at 3350 centimeter inverse. So why we are getting doublet at 3350 centimeter inverse, right? Because you see this NH2 group is there. So this NH2 will produce a doublet like your molar teeth, kind of W actually. Okay, so this doublet is due to the presence of the symmetric and asymmetric stretch of NH bond. Okay, so this signal basically which we are getting at 3350 centimeter inverse is due to the presence of symmetric, I am writing, I have confirmed this thing. And the resonating range in the IR spectrum of the NH bond is same as your OH, and it is at 3350 centimeter inverse. So this will resonate at 3350 centimeter inverse. And you are having this particular bands in the range of the 1600 to 450 centimeter inverse, which is due to the presence of the double bond present in it, right? It is very, very important. So you are having this, you are having a CH2, and then you are having this CH2. Okay, so this confirms this thing, right? So the most probable structure for this particular compound is this one. But you left with the, so you have explained this, you have explained these two, but you left with this singlet. Why this singlet is there? This is something very, very important, which you need to explain. Obviously, this singlet may be due to the presence of the NH2 group, right? And this is very, very important. The NH2 group in the proton NMR spectrum, basically the amine protons, they generally gives a broad singlet. However, this singlet is not very broad, but this NH2 gives a broad singlet. 1.2 ppm. 1.2 ppm. If you carefully look this is resonating at 1.2 ppm. And this was giving triplet. This is also giving a triplet. And this will give a singlet. And the chemical shift, generally the chemical shift of the NH proton is roughly 1.2 ppm, and you know the different hydrogens are present on the benzene rings as well. So these two hydrogens are of the same kind. In the previous classes I have explained this thing. Okay, so you see this hydrogen and this hydrogen, they are the same because they are having the same environment. uh, Here you can see at this position no other hydrogens are there, and in the bottom positions you are having two hydrogens, so these two have the same kind of the environment. And based on the same argument, these are the different kind of the hydrogens which are equivalent with each other but different from the Ha, because the environment of these two hydrogens is hydrogen on the bottom and two hydrogen on the top, right? So these are the different hydrogens, and this is your third set of the hydrogen. The environment of this hydrogen is only two, so these three groups are forming on the benzene ring, and this is the very common pattern of the mono substituted benzene. So the signal which you are getting at 7.1 ppm is due to these hydrogens. So you are getting at 7.1 ppm. Now you can see if I go back, you are having two triplets here. One triplet at say 3.6 and second one is 3.8. The signal at 3.6 ppm, and this signal that is triplet at 3.8 ppm. This signal will obviously be little bit upfield because this NH2 group is there, and this NH2 is electron pushing group, right? So it will push the electron onto this particular carbon atom and shield these hydrogens. So due to shielding, these hydrogens will be little upfield, while these two will resonate little downfield, because the circulating electron cloud will not shield these hydrogens much more strongly. This singlet, this is due to the NH. So you can say the two hydrogens are there. So please remember, it is very important. The signal is very broad due to the rapid exchange or the quadruple broadening from the nitrogen atom. So this is the most probable structure for this particular compound. I hope you understood the problem. Okay, now moving to the next problem. This is the problem number 22, and what it is saying: the following NMR spectra are monosubstituted aromatic hydrocarbons. So it is also it is already given in the question. It is monosubstituted aromatic hydrocarbons. That means this molecule is having the benzene ring and the carbon and the hydrogen with the formula of C10H11, which is given for this question. So there is no need to interpret this one, but I'll interpret this as well, right, for the beginners. So simply the problem is saying it is the aromatic hydrocarbon, and this proton NMR spectrum is given, and you need to interpret this one. What information is there? This triplet is given, and then this doublet is there, and then quintet is there, and then sextet is there, and these are the benzene ring protons. So immediately what you can do, you can write this benzene ring. Okay, and then different fragments which confirm this splitting pattern. Here you can see this is having the sextate. So how we can get the sextate? Say this is CH connected with the CH3, okay, and connected with the CH2. It is quite clear. You see here, three hydrogens are here, two hydrogens are here. If you want to calculate the splitting for this one, so you will apply the n+1 rule. N+1. So in the neighbor you are having 5 protons plus 1 equals to 6. So this will give you sextate. So now what you can do, you can decide the splitting pattern of this one as well as this one. So for this one, definitely you will get a doublet, because in the neighbor you are having only one proton. So you will write n+1. It's simply 1 plus 1 equals to 2. So it's a doublet. And one thing is sure, since this is producing a sextate, only CH3 and CH2 would be possible on the left and the right hand side, and there is no other substitution of the carbon atom on this particular carbon which is having the hydrogen again. So the pattern, you may conclude the benzene ring which is connected with the CH, and here this is your CH3 and this is CH2. Now it is quite clear this will produce a sextate due to the splitting by these 3 and 2 protons which I have explained here, and there is no hydrogen attached to this benzene ring. So basically this kind of substitution on the benzene ring is there. So this is producing sextate and this is producing a doublet. What you left with the quintet. Quintet means 5 splitting pattern of 5 different peaks. So how we can get the quintet? So for quintet, what we can do, we can put say CH3 here. Okay. So if I put CH3 here, you see, you are calculating for these two. So 3 hydrogens are here, or 1 hydrogen is here. So according to the n plus 1 rule, that is 4 plus 1 equals to 5. This will give you the quintet. It clearly indicates that CH3 is here. Okay. So this will give you quintet. So I am writing quintet for this. And then the last one, this CH3, definitely 2 hydrogens are on the left hand side. So if you apply the n plus 1 rule for this one, in the neighbor you are having only 2 hydrogens. So 2 plus 1 equals to 3. So this will give you triplet. And if now you see the different kinds of the hydrogens which are present here, I already explained to you in the mono-substituted benzene ring, this will produce a multiplet M which is resonating at 7.1 ppm, near about 7.1 ppm. So you have fixed this sextate, which is this one, right? And then the quintet, which is this one, right? And then a doublet, which is this one, and then again a triplet, which is this one. Now you can go for the chemical shift as well. So you can see here the most downfield signal will be due to the presence of the hydrogens on the benzene ring, which is resonated 7.1 ppm. So this signal, chemical shift somewhere around at 7.1 ppm. And you can see here this hydrogen, which is only one hydrogen, is connected with the benzene ring, and the circulating electron cloud of the benzene ring will cause magnetic anisotropy, and due to the magnetic anisotropy, this sextate will be very downfield, and you can see it is resonating at somewhere around 2.6 ppm. So that sextate will be there at 2.6 ppm, right? And then you are having this quintet. So quintet for this one, only 2 hydrogens are here, and on the left hand side 3 hydrogens are there. So the magnetic anisotropy effect will be more on these 2 hydrogens rather than these 3 hydrogens. So second downfield signal, right, will be this quintet, and you can see this quintet is second downfield signal resonating around somewhere at 1.6 ppm. So this quintet at 1.6 ppm. So I'm writing 1.6 ppm. Okay. And then you are having this doublet, and you know this doublet is due to the presence of this one, because magnetic anisotropy effect will be there for these 2 hydrogen in comparison to these 3 hydrogens, right? In comparison to these 3 hydrogens. So this will be next your third downfield signal, and that would resonate around somewhere at 1.2 ppm. So you can write the chemical shift for this one, 1.2 ppm, and your last signal somewhere around 0.8 ppm, which is this triplet. Okay. So this is the most probable structure given for this particular compound. You can take the screenshot because I'm going to solve the next problem. Okay. So I hope you have taken the screenshot. Now I am moving to the second part of the problem. So second one is also the isomer C10H14, and it is also the monosubstituted aromatic hydrocarbon. So one thing is clear, you are having the benzene ring. So now you can see here again you are having the sextate, and for the sextate, if you want a sextate for this CH, there must be the presence of the 3 hydrogens on the right or the left hand side, and 2 of the hydrogens on the right or the left hand side. Anywhere you can put, I am putting on the right hand side. So like the previous problem, it will give you a sextate. There is no problem in that. Okay, and definitely this will give you what? Your doublet. So I'm writing D for this one. So you have confirmed this sextate. Okay, and there is no doublet. Please remember, there is no doublet. When doublet is not there, that means this cannot be your straightforward CH3. Well, you are getting a two triplets. So that means CH2 connected with the CH2, one triplet, and then again it is connected with the CH2, right? So if you check the splitting patterns, so for this you will get N plus 1 rule. In the neighbor carbon you are having two hydrogens. So for these two hydrogens you will write 2 plus 1 and this will give you a triplet. Okay, particular for these two hydrogens on the right hand side, two on the left hand side. If you apply the N plus 1 rule, 1, 2, 3, 4, 5, right? This is a quintet. However, the exact shape of quintet is not like that. It is according to the originally it is according to the Pascal's triangle. Okay, and for this one, if you connect with this one, again it will give you the triplet. Now you see, quintet you have proved, two triplets you have proved, what you left with the one of the sextate. So how this sextate is there? This is something very, very important which we need to clarify. So for this, what we can do, we can put CH3 here. So if I put CH3 over there, so this will also give you the triplet. If I do this, right, then definitely this information is wrong. Why? Because three hydrogens are here and two hydrogens are here. It can never be a triplet. So what we can do, we can delete this. So N plus 1, on the right hand side 3 hydrogens, on the left hand side 2 hydrogens. So it is nothing but 5 plus 1 equals to 6. So this will give you sextate, triplet. So two fragments are there, fragment number 1 and fragment number 2. And if you put these fragments together, getting a triplet. For this one, you will get a quintet, that is 5. Okay, and for this one you will get a sextate, and for this one you are getting a triplet. And what information we can get from the chemical shift values? You can see the most downfield signal is that 7.1 ppm. Obviously this is due to the presence of these hydrogens which are connected to the benzene ring. The second one is the triplet one. Now you have to decide, you are having two triplets. One triplet is this one, another triplet is this one. Since you are having the two triplets, now it is your duty to decide this chemical shift, right? Which this belongs to, whether to this triplet or to this triplet. Now it is quite clear, due to the magnetic anisotropy of the circulating electron cloud, these are very, very downfield, right? When they are very, very, very downfield, that means the triplet which is resonating at 2.8 ppm due to this CH2. Okay, so you can write this is 2.8, this particular signal, right? This particular one. And then you can see here this quintet is quite fine, the second one, and then sextate is again very fine to this one, and the triplet is very fine due to this one, because magnetic anisotropy, the effect of the magnetic anisotropy keeps on decreasing when we move throughout the chain from the from the left to the right. So magnetic anisotropy will be most due for this one, so that's why it is very, very downfield, and least for this one, that's why it is most upfield, which is this triplet. So this is how the proton NMR spectrum are useful in deciding the two different isomeric structures. Okay, so if you understood the thing, likes the lecture, please give thumbs up to the lecture, and if you are watching video for the first time, please subscribe the tetrahedron chemistry classes and do share with your friends as well. So that's it for today. I'll meet you in the next lecture with different problem. Okay, thank you very much.